Hello students, welcome back to JCE Connect series of lectures. In previous lecture, we have solved some numerical problems on moment carrying capacity of laterally restrained beams. So in this particular session also we'll take one more example and try to understand laterally restrained beam, how the moment capacity can be calculated for a laterally restrained beam. And in this particular session, whatever example I am taking, it is bit different from the previous examples. So in this numerical example, what is been given, let us see, determine the load carrying capacity of ISMB at 1.202 kilonewton per meter used as a cantilever beam of 3 meter effective span. So this is the first part. So they asked you to calculate what is the load carrying capacity of ISMB 600. That ISMB 600 is being using as a cantilever beam. And after calculating the load carrying capacity, so they asked also check for shear, web buckling, web crippling, and assume stiff bearing length B1 is 270 mm. This is given, and also you have to calculate or you have to check for deflection. Take Fy 250 Newton per millimeter square and Young's modulus for the given section E is equal to 2 into 10 raised to 5 Newton per millimeter square. Students, here try to understand the section given here is ISMB 600, and this section is being using as a cantilever beam in one of the steel structure. And the question here is, what is the load carrying capacity of this member? How much is load it is carrying? And if that is the case, means if it is carrying the load, then for that load you have to check whether it is able to carry the shear, that is check for shear, and also what is the strength in buckling, whether it is able to sustain the load. Then web crippling, what is the strength, that is a crippling strength to be calculated. Then finally you have to calculate the deflection. So generally this type of problems will be asked for 15 marks problem. This is asked for 15 marks. Sometimes directly you may get for 20 marks also. So generally 15 marks problem. This problem is for 15 marks in exam. And let us write the first given data. The data given here is that is ISMB section is been given, and you have to refer the steel table. And for this ISMB 600 at 1.202 kilonewton per meter, this is a self weight of the ISMB 600. And this always whatever the section is been mentioning, it is been mentioned with the along with the weight also. Okay, so this particular section you have to refer in a steel table. So and take the properties, all the properties from the steel table, that is a depth of the section, then width of the flange, then the thickness of the flange, thickness of web, then the root radius. So it will be generally like this I section, okay. So this will be depth of the section, this is the flange width of the section, and this is the web, and this is thickness of flange, and this junction right section, this is the root radius. This also you will get from the steel table. And even you can get the elastic section modulus from the steel table also, but except this plastic section modulus, you have to get from the IS 800 2007 page number 138. Page 138, you have to refer page number 138. There you may get all the properties in the IS 800 2007 like this, but some properties may not be given in this IS 800 2007. For that you can refer steel table and take it. R1 cannot be given in IS 800, so for that you have to refer the steel table and get the value. Then also the moment of inertia, if you are taking, this is a major axis, this is a z axis, then moment of inertia about this axis, that is IZZ, this value also we required when we do check for the deflection. That time you required this value. Okay, so first list all the properties of the section by referring steel table or by referring IS 800 2007 page number 138. Just note it down all the properties. Once you noted all the properties, then the next step is what? Next step is, as usual, you have to do the section classification based on the ratios of different elements. You have to do the section classification. That means, as you know, the section classification, that is whether the section is lying in plastic or a compact or a semi-compact or slender. So let us check the section classification. Just take the depth of the web, that is D, and you know how to take the effective depth of the web for the section classification. On section classification we have solved some numericals. Just you refer previous lectures and all, you will come to know how the section classification has been done. Then take the depth, that is h minus 2 into thickness of a plus r1. So these all you have noted down from the steel table. Substitute here, you will get this one. Then the outstand of flange, according to the IS 800, you have to take the outstand of flange, that is half of the width of the flange. So you will get this much and this much. Then epsilon also you have to note it down, root of 250 divided by fy, you will get the value 1. Then according to table number 2 of IS 800 2007, so if we want to classify section, you have to take the individual element ratios, that is flange is one element and web is another element. So here in this particular section, you have to take the individual elements. So you have to take this as a flange up to this P, and effective depth to be taken. So up to here, this is represents the depth. So you have noted down all. Then you take the ratios. So calculate the ratios. So we have got ratio this much, but the permissible limit is this much for the plastic section, and this is for a flange element and this is for the web element. So both, this is also represent the plastic section, this element, and this is also representing the plastic section. Hence we can write according to the table number 2 IS 800 2007. So here what we can write, hence the section is classified as a plastic section because this is less than 9.4 epsilon and this is less than 84 epsilon. What it represents according to the code, as I explained previously, table number 2 of page 18. If you refer page 18, table number 2. So I'll show here IS 800. Just look at this table number 2. What has been given here? Limiting width to thickness ratios. So compression element, we have for in our case, so we are having a rolled section, and you have to take the ratio of width to thickness of flange. The class 1 section is 9.4 up to 9.4. Then that element is being classified as a plastic section. If it beyond 9.4, you have to consider it as a compact section. If it is beyond 10.5, you have to consider it as a semi-compact section. I mean, if it is beyond that one, then it will be a slender section. So here you need to check individual element. So that is a flange element and the web element. So here the figures are being given individually. You have to check that is whether the flange is in a plastic or the web is in a plastic. You have to check individual element classification. But in our case, what we are getting here, the given section is plastic section. Hence further, whatever the section you are going to design, it will be considered as a plastic section. According to that, you have to design. Next, once you come to know the given section is a plastic section, then for a plastic section, the beta B to be taken 1 for a plastic section. Then what is the design bending strength MD to be calculated, and MD formula, as you know, beta B ZB into Fy by gamma MO. So these all values you know, substitute here, then get the bending strength. This is the bending strength, 797.87 into, sorry, actually this is 797.87 not 10 to 3, 797.87 kilonewton meter only. This is only kilonewton meter. This here 797.87 into 10 to 6 Newton millimeter. Then when you convert in kilonewton meter, this will be 797.87 kilonewton meter. Then, but whatever the bending strength you have calculated previously, that should be less than this much for a cantilever beam. As you know, this one, this condition, this check you have to do, this should be less than 1.5 times of ZE into Fy. Again you substitute, just calculate this value here, this value you have to calculate. So we have got that value as 1043.31. Compare with the previous value. So whichever is the least one between that one, that is to be considered as a design bending strength. Hence the given section bending strength will be this much. That is ISMB 600 can resist the bending up to 797.8 kilonewton meter. This is the bending strength of ISMB 600. Now once you come to know the bending strength, then let us calculate the load carrying capacity of that section. So let us take the W is the factored load, that is a UDL to be considered. Hence that UDL we have taken in a kilonewton per meter. So since in this problem the beam acting as a cantilever beam and it is being subjecting to UDL of W, which is in kilonewton per meter. Whatever the load you are putting on this cantilever beam, that is in kilonewton per meter, and this cantilever having a span of length 3 meter. It is being given in a problem. And as you know, for the cantilever beam, from the strength of material, you know the maximum bending moment for a cantilever beam carrying a UDL, we know that M is WL square by 2. So maximum bending moment, we know this one, WL square by 2. Then equating this moment, bending moment, with the design bending strength whatever we have obtained. So if we equate this one, we get the load carrying capacity of the member. Just equate, because we know this formula. This is the bending moment, that is maximum bending moment for a cantilever beam which is carrying the UDL. Then equate this to this one. Okay, so equating, then we get finally the load carrying capacity, that is 177.30 kilonewton per meter. This is the factored load. So whatever this one you have calculated, this will be factored one. Okay, so once we know this one, let us check the shear. So very easy. Check for shear next. And as we know, maximum shear force for cantilever beam carrying a UDL, so maximum shear force will be at support here. We know the formula V, so this maximum shear will be WL by 2. So it's very simple. So as we know the maximum shear force for cantilever beam carrying a UDL, the V will be this one, V equal to W into L. And we know W calculated previously, and we know the span length. Substitute here and get the shear strength. This much is the shear actually acting. Then what is the shear design shear strength for the section? So whatever the section we have assigned, how much it is capable to carry the shear strength. So that is design shear strength. This shear is actually acting in a beam, and whatever this shear we are calculating, it is how much is the design shear strength resisting by the given section. This is the formula we know, Vd equal to Av into Fyw divided by root 3 gamma mo, and this Ev is the shear area. Since it is a hot rolled section, then Av can be written H into Tw, that is the overall depth into thickness. You have to take the overall depth into thickness. So that is in this one, you have to take the overall depth up to here into thickness of web. Okay, so overall depth into thickness, calculate that area, then Fyw is the yield stress of web material, then substitute here, that is the design shear strength we got 944.75 kilonewton, which is more than 531.9 kilonewton, hence safe. But according to code, what it says, 60% of the design strength to be considered. So hence the 60% of the design strength will give us this much is the shear, and this also greater than the obtained shear. Hence we can write the section is adequate to resist the shear. Suppose if you are getting less than this 60% of design shear strength is less than the actually acting shear, then we need to take the precautionary measures. That is, you have to provide the stiffness and all, then that design steps will differ. Okay, so hence we can write here the section is adequate to resist the shear. Then after this one, the next is a check for web buckling. So we have checked previously the shear, so it can resist the shear. Next is web buckling. As you know, what you mean by web buckling, and we have discussed about the web buckling and all in previous lecture. So this is the overall buckling. We can say it is the overall buckling of web due to the concentrated load, or you can say due to the support reactions, we get the overall buckling like this. Like this we get the buckling. So how much is buckling strength we need to calculate for this one? Buckling strength, for this one, this is the formula we know, we have discussed previously how to calculate the buckling strength, that is a design buckling strength. This is a B1 plus N1 into TW into FCD, and this B1 is a stiff varying length, and you have discussed previously. Let us look at this figure here. In this figure, so it has buckled like this, and at the middle it has a very high compressive stress. Usually it buckles overall at the middle, and at the middle it will be having a very high stresses, and because of the support reaction and because of the concentrated load acting, this buckling may takes place. Okay, so up to this one we have to take it as a bearing length B1. It is been given in a problem, and N1 to be calculated based on the load dispersion up to the middle of the section. It is dispersing at an angle of 45 degree, and about this one we have discussed previously how to get the buckling strength and all. So just refer that lecture and you will come to know how to calculate the buckling strength and all. So here the P1 is been given 270, just note it down here, and N1 to be calculated, that is half the depth of the section, 600/2, then the thickness of web is given. Then FCD is the design compressive stress. This FCD to be calculated based on the slenderness ratio of the web, and this slenderness ratio for this web is we have derived the equation previous lecture. Please refer that video lecture, and there we have derived while calculating the buckling strength. So this is the lambda for that web, we get 2.5 times of H into TW. Then this is a slenderness ratio 125 we get here. Then from table number 9C of IS 800 2007, if you refer there, it's been classified as a buckling class C, table number 9. I will show the table number 9 here. Table number 9, 9C, table number 9C. If you refer table number 9C, so what has been given here? Design compressive stress FCD for column buckling class C. Means for column it will be a buckling class C. Since the web is acting as a column here, so you have to consider this as a class C only. So you have to refer table number 9C. Remember table number 9C, page number 42. In this column it represents the slenderness ratio, and this here, this one yield stress, it represents the yield stress, and here yield stress has been given 200, 210, 220, 230, 240, 250. But in our case we are taking yield stress as a 250 material yield stress. Then this is the slenderness ratio, and here in our case in this problem it is lying between 120 and 130. So for 120, so for 250 what is this? 83.7, and 130 it is 74.3. It is lying in between, so you have to interpolate this one. You have to do the interpolation, so get the compressive stress for lambda equal to 125. So I have referred table number 9C, IS 2007, so where the lambda is given 120, 83.7 Newton per millimeter square. It is actually Newton per millimeter square. This is also Newton per millimeter square. This is a stress. Then for 120, 83.7, for 130, 74.3. So for 125, how much? So interpolate. Then I interpolated. So here I got compressive stress, design compressive stress as a 79. I hope you have understood this one. Okay, so it is very easy. Just to calculate the strength, you have to calculate the slenderness ratio. For that slenderness ratio, refer table number 9C of IS 2007, page 42. Okay, then after this one, calculate the bending, that is buckling strength. So we have got buckling strength this much, hence it is greater than 531.9. So hence the web is safe against buckling. If suppose if you are getting less than this one, you have to say stiffeners are required for the web against buckling. Okay. Similarly, check for web crippling. So again we know the crippling strength of web. So crippling strength of web. So what do you mean by crippling? So heavy concentrated load, it will cripple like this, heavy concentrated load or support reaction like this. So either the heavy concentrated load like this, it may cripple here like this, or under a reaction like this. So these are the reaction. So under a reaction transferred by a flange, the flange is being transferring the reaction here, transferred by the flange to the thin web. The web is very thin. So heavy reaction or the concentrated load is being transferred by a flange to the thin web. Then the effect of concentrated action, this effect of concentrated action shall cause the local buckling of web in the vicinity of reaction or the load. Then the web is being crushed like this. It is called as a web crippling. Now, so to avoid that one, we have to disperse the load in wider area. So here the stiff bearing length is been given, that is B1 is been given in the problem. So it is given as a 270 stiff bearing, and in web crippling the load is being dispersing at a slope of 1:2.5. It has been given in a code. So to disperse the load at 1:2.5 slope, this is the slope. Then this one represents the web thickness. This is the web thickness, and this is the root radius. Okay, this is the root radius R1, and it will be passing through the flange and root radius like this at a slope of 1:2.5. So with respect to this slope, you have to calculate the N2 value. Okay, so if I construct a triangle here, so I'll get like this. then this will be N2, this is theta, and this will be what? This total thickness will be what? Thickness of flange plus R1. I get this one. Okay, then how to get N2? This is tan theta equal to opposite by adjacent. Then opposite is what? Thickness of flange plus R1 divided by N2. Then I'll get a N2. So I'll get a N2 as, that is thickness of flange plus R1, because tan 45. Suppose if you take this one is this one, so you'll be getting 2.5 into TA plus R1. Okay, because at this ratio it is dispersing, then you will get 2.5 into TA plus R1. Okay, I hope you understood this one. Then substitute here 270 plus 2.5, 20.8 plus 20 into 12 divided into 250 by 1.1. Then the crippling strength we get this much, which is greater than 531.9 kilonewton, hence safe in crippling. You can say the safe in crippling. Okay, so next will be what? Check for deflection. Check for deflection. And for cantilever beam, maximum deflection, we know the formula. This is the maximum deflection the cantilever beam gives, WL raised to 4 divided by 8 EI. So that is the maximum deflection that you get here. Delta max, then WL raised to 4 by 8 EI. Then where W to be taken here is a working load, not a factored load. So for working load you have to check the deflections. So hence you have to divide it by 1.5. 177.3 divided by 1.5, that is the load carrying by the cantilever beam, divided by 1.5, you get this much. Then calculate the maximum deflection, substitute here. So we have taken all in millimeter, then substitute here, you will get the delta max as 6.51 millimeter. But allowable deflection as for the code, delta should be L by 150. So this much is allowable. So hence delta max is 6.51. We are getting it, which is less than L by 150. Hence okay. So it is safe in deflection. So therefore design satisfies all the conditions. Hence load carrying capacity of member will be 177.3 kilonewton per meter. Okay. So this is the way how to calculate the bending strength and how to do the checks, step by step check for shear, check for web buckling and web crippling. So try to refer previous lectures where we have been discussed about the bending strength calculation and web buckling, how the web buckling strength can be calculated and web crippling strength can be calculated, and use those equations. Just to remember those equations, or else you refer IS 800-2007 where you will be getting the equations there. Okay, I hope you understood this one. Again we'll continue next class some design problems. So design problems means where the load will be given for the given loading condition, how the member can be designed. So we'll we'll continue next class. And even the determination of design bending strength for the given beam section. So for the given beam section, how the design bending strength can be calculated, or the design or the given loading, how the beam can be designed. We'll continue with that next class. Thank you.